right, hello and welcome. We're here today to talk about sodium and lithium ion batteries. So first we're going to start by introducing lithium ion batteries, then we'll talk about sodium batteries before we compare the two and talk about sodium battery research. So the first battery was stacked discs of copper and zinc, and they were separated by cloth, and then either end was connected by a wire which produced a current and made a battery. Then came the lead acid battery, which really paved the way for rechargeable battery technology. In fact, it's still used today to start most internal combustion engine cars. After that came the lithium ion battery, which is where lithium was combined with a transition metal, and then it would let a lithium ion migrate from one electrode to the other, which made it a rechargeable battery. Now, depending on the transition metal that was used, the battery could have a higher potential, but could also be susceptible to thermal runaway, which is where an increase in temperature changes the conditions of the battery and then leads to another increase in temperature, and it just kind of gets away from you from there. So a really great example of this was when Sony made lithium cobalt oxide batteries in the 1990s. These were really susceptible to thermal runaway and would often catch fire. But since then, other more stable forms of lithium ion batteries have been invented and have begun to dominate the industry. Now, obviously with lithium batteries, you need a lot of lithium to be mined. So in South America, there's what's called the lithium triangle, which contains parts of Chile, Bolivia, and Argentina. And then in this triangle, there's over half of the world's supply of lithium, which is contained beneath salt flats. And the mining uses a series of evaporation pools, which requires 500,000 gallons of water per ton of lithium. Obviously, this can be a really big problem because that's a lot of water, and a lot of these areas are already really dry. In Salar de Atacama in Chile, which again is a very desertous, dry area, mining consumed 65% of the water supply there. This can be really bad for farmers in this area where some of the communities already have to get water driven in from elsewhere. On top of that, toxic chemicals like hydrochloric acid can leak into the water supply. And even in places like Australia and North America, where there are more traditional methods of mining used, it can still require the use of chemicals. For example, in Nevada, research found that mining impacted fish as far as 50 miles downstream from the operation. On top of all of this, mining can also harm the soil and cause air contamination. One way to kind of mitigate the effects of mining is by recycling the batteries. Not only are you requiring less materials now because you're recycling them, but you're also going to drop the manufacturing prices and therefore also the prices of the batteries themselves. It also reduces the amount that makes it to the landfills. So there are certain metals in batteries that can readily leak and will contaminate the soil and groundwater, which can really threaten ecosystems and human health. The problem with recycling is that there's not a whole lot of research on it. The plants are very expensive and require a lot of energy. And even with all of that, they still don't cover all of the valuable battery materials. So for that reason, most batteries just don't get recycled. In Australia, only about 2 to 3% of batteries get recycled. And in the United States and European Union, only about 5% of lithium ion batteries are being recycled. But there are projects to improve recycling of these batteries. In January of 2019, the Department of Energy announced a lithium-ion battery recycling R&D center. And then in 2020, the UK created a consortium which was dedicated to recycling lithium-ion batteries and brought together scientists and engineers from various institutions.
So the detriments of using lithium batteries have always been apparent, even since the very beginning. So scientists and engineers have always worked on alternatives to lithium. One of the earliest chemicals studied to potentially replace lithium was that of zinc. This element is naturally found and rather abundant compared to that of lithium. It is stable and low cost, but not as powerful as lithium, and studies have shown that zinc reserves might be completely diminished in the near future if battery production were to shift to zinc alternatives. Another alternative would be hydrogen fuel cells, which are promising in that they're low cost and environmentally friendly, but the main issue is that they are highly flammable and expensive to store. So long-term conversion to hydrogen fuel cells could be detrimental to the safety and well-being of workers creating the cells. The sodium-based battery is one of the most promising looking replacements to lithium, as it is stable, unlike the hydrogen cells, and will not be used up as quickly as zinc. The sodium battery is significantly cheaper to manufacture and leaves much less of a carbon footprint in consideration to mining, extraction, and production. It is interesting to note that research on a sodium-based alternative has already started around 50 years ago, but now more than ever, we are much closer to finding the right chemical combination of sodium to reach the same level of electrical output as a lithium-based battery. There is a sodium and myo-inositol battery makeup that looks very promising. As of right now, the battery is just under the energy output of typical lithium batteries. The science behind this battery is fascinating when it's broken down. Sodium makes up the cathode of the battery, which is where electrons are stored. The electrons are then shot into the anode, this case being myo-inositol, and the constant flow of electrons is what discharges electricity and power.
Cost comparison. As research into sodium batteries continues, the cost when compared to lithium batteries has dropped significantly. One key reason for this is the availability of sodium versus lithium, with sodium being the sixth most common element in the Earth's crust. Lithium batteries also require copper in the anode, while sodium batteries can use the cheaper aluminum. Lithium batteries also require cobalt, a rare and expensive element with a variably secure supply chain. Energy storage comparison. Lithium batteries allow for far greater specific energy with up to 220 watt-hours per kilogram of material in the battery compared to sodium's 90 watt-hours per kilogram. Lithium batteries are also significantly more energy dense, with experimental sodium batteries able to reach around 50% of a comparable lithium battery. Sodium batteries do not provide the same power as comparable lithium ones, losing about 10% due to a 0.3 volt lower voltage. Environmental and ethical concerns. Mining operations account for 16% of a battery's total energy cost, with cobalt, lithium, and manganese mining causing significant pollution from both fossil fuels and wastewater. Comparatively, sodium is far easier to obtain, whether by traditional mining operations or seawater evaporation. Ethical concerns are also rampant in the production of lithium batteries, most notably the long history of exploitation of cobalt miners in the Congo. Sodium, however, is widely available and does not require cobalt to function. It comes straight out of the ocean. The motivation for ongoing projects. Sodium batteries will always remain an alluring prospect, while lithium batteries maintain market share. Lithium mining operations are inconvenient, expensive, and hazardous to the environment. Sodium is easily extracted and purified from seawater, as you can see in these drying pans here. I say pan, but it's really just an enormous field next to an ocean. Sodium is easily Go back. Thank you. Sodium is easily extracted and purified from seawater and natural deposits with very little of those concerns. Ongoing research questions. Since 2010, a major challenge in the production of a consumer sodium battery has been the search for cathodes with sufficiently high energy density. A current candidate is a sodium-iron coordination compound with hexacyanoferrate. A family of similar chemicals known as PBAs have been patented and are in preparation to be commercialized by Novasys Energies, Inc. You've got some zinc and graphite anodes there. Ongoing research and results. Unlike a lithium battery, the greater size of sodium ions prevents a simple porting over of techniques devised for use in lithium batteries. It has been found that while the sodium ion is too large to achieve desired current times time density using a graphite electrode, it is possible to manufacture a similarly optimal material from non-graphitic carbon. This amorphous carbon has been experimentally demonstrated to achieve current times time densities of roughly 80 to 100%, those of densities in lithium-ion batteries that use graphite electrodes. Future prospects. Since 2020, the prospect of a semi-solid flow battery using sodium has been in consideration. This is unlikely to be seen within the decade, but it has the potential to help overcome limitations in the energy density of current sodium battery designs. Current designs would limit energy density of sodium batteries to less than 50% of lithium capacity. Conclusion: the lithium-ion battery is made of lithium and a transition metal. An alternative to the lithium battery is to use sodium, another alkali metal. There are many advantages to sodium batteries, and research is currently being done and planned for to further explore the sodium battery. Thank you, guys. These are our references.